Hello and welcome. And I'm very pleased that to introduce this fourth session of the Applied Urban Modeling Symposium of 2020. And for this session, we truly have gone global, and this is currently broadcast on Facebook and also on China's Bilibili website. And for those people who are listening, hello and welcome. And we're particularly grateful for the support that and help from Professor Yue Ying and her student, Luo Qiuyu, who actually helped us both to make the contents accessible on the WeChat pages, which you should be able to find now from the Shenzhen University's website, the WeChat site, and also, of course, the material is also available for our own website at the University of Cambridge. And afterwards, all of the information, including the recording of the formal part of this session, will be available on our SMS video website. And so we're very excited today to make possibly the first engagement with another really truly inspiring tradition of spatial econometrics, particularly in applying spatial econometrics to real data and the real historic events. And for this, I will hand over to my colleague, Dr. Jamil Noor, who is going to introduce the speaker. Thank you.
Thank you, Ing. Good afternoon, everyone. Good morning. And for those connecting from the West Coast, and good evening for those connecting from the East Coast. My name is Jamil Noor. I'm a labor economist turned urban economist, working as a postdoctoral researcher at the Martin Center. And it's a great pleasure to welcome Professor Stephan Heblich, who is one of the most quoted economists in this field. So we are very lucky to have him today. Let me just briefly introduce Professor Heblich, who is has worked extensively in areas from international trade to productivity growth and heterogeneous firms. He currently holds the Shapiro's chair at the Princeton University as professor in economics, and is also director of the International Trade and Investment Program for the NBER, the National Bureau of Economic Research. He previously taught at London School of Economics and Yale School of Management, and he recently was awarded the Frisch Medal and the Bhagwati Prize. I might add to what Ing said that Steve Heblich is one of the founding members of a new field in urban economics, quantitative spatial economics, which brings data precision to the estimation of forces that have been known for decades by economists, but have always posed challenges because of a variety of endogeneity issues. The talk from Steve Heblich today, The Making of the Modern Metropolis, Evidence from London, combines the summa of the literature in urban economics and estimation of agglomeration effects and transport effects in growth and specialization of cities. And I welcome you to pose any questions that would allow a bridge between the traditional fields in transport theory and the land use and transport interactions to this exciting new field of quantitative spatial economics. Steve, the floor is yours.
Thank you very much. Thank you very much for that generous introduction. And thank you so much for the invitation to present today. There are so many connections between the field of economics, urban planning, and other social sciences. And I think this is a wonderful initiative. And I'm very grateful for the opportunity to being able to interact and hopefully exchange ideas and stimulate new research projects through this initiative. So thank you, Ying. Thank you very much for the invitation, and thank you for the introduction today. So the project I'd like to talk about today is called The Making of the Modern Metropolis, Evidence from London, and it's a joint paper with Stephan Heblich and Daniel Sturm. And it's really, as you said during the introduction, it's really trying to bring together the kind of models that urban planners and economists have been working with for many decades, and then really confront them with the data and try to show that these models actually have explanatory power, that they're quantitatively successful in predicting what happens in the data, and they can be used to evaluate the counterfactual effects of a variety of policies. And so what's the broad motivation for this talk? Well, as we all know, modern metropolitan areas involve immense concentrations of economic activity. So London, for example, today houses around 8.4 million people. And we don't often think about it, but before COVID, every day, modern transport networks involve moving millions of people around cities every day between where they live and where they work. And so, for example, the London Underground alone would typically handle around 3.5 passenger journeys each day, and its trains each year travel something like 200 times the distance between the Earth and the Moon. So sort of amazing movements of people around these modern metropolitan areas. And so the thing that motivated us in this project was really trying to understand what role does this separation of workplace and residence play in understanding these concentrations of economic activity. And it's obviously only because we can separate workplace and residence that we can create dense concentrations of employment districts and potentially realize agglomeration economies from concentrating economic activity together there. And it's only because of that separation that we can create distinctive residential amenities with their local amenities for the residents of those neighborhoods. And so we really want to sort of understand what role that separation plays in enabling large modern metropolitan areas to emerge. And so what we're going to try to do is try to provide new evidence on their role in agglomeration using a combination of three things. Firstly, we've put together a novel, new, spatially disaggregated data set on economic activity in the London area from 1801 through until 1921. Secondly, we're going to exploit a natural experiment, the invention of the steam passenger railway, and I'll say more about that in a second. And then thirdly, relating to the motivation we started with, we're going to try to bring a quantitative urban model of the organization of economic activity within the city and try to see to what extent this model is actually successful in explaining the impact of this new transport technology and what that implies about the underlying strength of agglomeration forces that underpin these concentrations of economic activity. And so the basic idea behind the model is extremely simple behind the whole paper, namely that steam railways for the very first time made possible a large-scale separation of where people live and where they work. Prior to that, when human power and horsepower were the main sort of sources of motive power, it was extremely costly to separate where you lived and where you worked. And so most people lived very close to where they worked, as I'll show you later in the data. And so we think this sort of empirical setting of looking at London and the invention of the steam passenger railway is kind of an exciting setting, has a number of advantages for trying to look at the role of modern transport technologies in facilitating a separation of workplace and residence. So in 1801, at the beginning of our sample period, London housed around 1 million people, but it was still a walkable city of around 5 miles from east to west. And it wasn't radically different from other large cities that had emerged throughout history, such as Beijing at that time, ancient Rome, other large cities. Yet by the turn of the 20th century, towards the end of our sample period, London housed over 6.5 million people. It stretched from 17 miles east to west. And it was the sort of modern metropolis we would recognize today on a dramatically larger scale than any other city up to that point in human history. And as I said, this period also includes this sort of dramatic change in transport technology that we want to leverage to see to what extent our models can explain the effects of this new transport technology. As you all know, steam railways were initially developed to haul freight at mines at the Stockton to Darlington Railway in 1825 in England, and they're only later applied to transport people, and in particular, the London and Greenwich Railway in 1836 was the first dedicated steam passenger railway. As well as having this sort of exciting empirical setting with this large-scale experiment, we think there are a number of attractions about the set of models that we're going to take to the data. In particular, one of the things I'm going to emphasize today is the way we structurally estimate the model. We can apply it even though we only observe bilateral commuting flows between locations at the very end of our sample period in 1921. So in 1921, England and Wales population census was the first to collect detailed data on the bilateral flows of people from where they live in their residence to where they work in their workplace, and we'll leverage that heavily in our analysis. But even though we can only see those data at the very end of the sample period in 1921, we're able to use our model and undertake comparative statics for the effect of removing the railway network, so eliminating this innovation in transport technology, and generating predictions from the model all the way back in time to the very beginning of the 19th century. We think that's pretty exciting because it means this methodology can be used in many other contexts where you only have bilateral commuting data in an initial year, and you're interested in working out what might happen in future years or in previous years, departing from that baseline period. Another kind of strength of the methodology we're going to implement today is we're going to combine those commuting data in our baseline year with some earlier data in historical years, namely the number of people who live in each location within London in every year back to 1801, and the value of land and buildings in every location in London all the way back to the early 19th century. And having those earlier historical data is absolutely crucial because together with the commuting data in our baseline year, it's going to enable us to look at the effect of the new transport technology while controlling for the many other things that happened in London during the 19th century. So obviously over the course of the 19th century, productivity likely changed in every location in London. The amenities those locations had to offer changed, including, for example, the public health environment. Railways not only affected the ability of people to commute between where they live and where they work, they also affected the cost of trading goods between locations. And a key strength of our methodology is because we have those commuting data in the initial year and those earlier data on population and land values, within the model we develop, we're able to control for all of those other things that changed over time. How is it possible for us to do that? Well, within this class of models, it's going to turn out that the observed data on population and the value of land and buildings are going to perfectly control for all of these other things that changed. And so I'll explain why that's the case and how that works later. And so we think, again, that's a sort of exciting feature of the methodology that has applications in other settings. Another product of it is that, just by observing the commuting data and the historical population and land values, we're going to be able to use the model to predict historical employment by workplace data back to the early 19th century and historical commuting patterns, even though in general, we don't have in the data historical workplace data all the way back to the early 19th century. And so we're going to be able to use the model to solve a sort of missing data problem for us. And I apologize about the noise in the background. There's some sort of work being done in the house next door to us. I apologize for that. Hopefully it'll subside relatively quickly. And so we're going to be able to use the model to solve for this sort of missing data problem for us. Nonetheless, for a couple of locations in London, we have a little bit of historical data on employment by workplace and commuting patterns. And so we'll use those as an over-identification check on our model's predictions. And then finally, the way we take the model to the data is going to have a recursive structure about which I'll say more in a moment. And so what that means is we're going to be able to proceed step by step, where each step involves additional marginal assumptions. Obviously, what we're doing contributes to a very large literature in economics and urban planning on the organization of economic activity within cities, and we're very much building on that prior research. So I'm going to try to talk for sort of around another 10 minutes about introducing the data and providing a little bit of evidence to you that something interesting happens in London around the time of the invention of this new transport technology. And then I'm going to take a pause to take some questions and engage in some discussion and debate. and then sort of start again and then introduce the model and show how we can take it to the data and try to explain these sort of patterns that I'm going to reveal in the first part of my talk. So we put together this new spatially disaggregated data on economic activity in London over more than a century, from 1801 to 1921. I should acknowledge, especially speaking today at Cambridge, we're benefiting tremendously from the Cambridge Group on Population and Social Structure, which has played a big role in digitizing the historical population census of England and Wales. And so that's going to be one of our key data sources, is going to be population by residents in every parish in the Greater London area from 1801 through to 1921. And so whenever I refer to GLA during my talk, I'm going to be talking about the Greater London area. That's the modern day boundaries of Greater London, for which we've constructed this historical data for every parish within those boundaries going backwards in time. Around 285 of them, so pretty finely detailed spatial data. And then we also have some variables at a slightly more aggregated level of what are termed metropolitan boroughs, which are aggregations of these parishes to around 99 metropolitan boroughs in the modern day Greater London area. As I mentioned, another key piece of data for taking the model to think about the effect of this new transport technology is going to be bilateral commuting flows that we have in 1921 between these 99 boroughs within the Greater London area. Before 1921, we don't have data on employment by workplace. We only have information on where people live by residence. And so, as I mentioned, the model will solve that missing data problem for us. But we do have a little bit of historical data on employment by workplace that we can use as a check on the model's predictions and to check the sort of explanatory power and success of the model. And we think that's a sort of an important feature of our application. And in particular, we're going to use some data on employment by workplace from what were referred to as the City of London day censuses, which were conducted from 1866 onwards. And so in contrast to the population census, which, as you all know, records population where people sleep on census night, so it's a census of the night population. In contrast to that, the City of London actually conducted these censuses of the number of people present during the day. And so we can use those as a check on our model's predictions. And then we also have a little bit of historical commuting data that we'll again use as a check on the model's predictions. Another key piece of data which makes our whole approach possible is that we have data on the value of land and buildings in each one of these parishes back to the early 19th century. They're data that we digitized ourselves using sort of detailed records actually compiled by the House of Commons and the House of Lords back to the early 19th century. And then obviously we've also got rich data on the transport network over time. So just to give you a sense of our data. So, you know, as you all know, this is the area here of Greater London. So here in red, these are the boundaries of the modern day Greater London Authority. And they've been placed here in the wider home counties, which are shown here by the outer dark black line surrounding the home counties. So red is the modern day boundaries of the Greater London Authority. In purple here, we've got the boundaries of the slightly smaller historical county of London. And then barely visible at the very center of the screen, we have the boundaries of what is referred to as the City of London, which is the historical commercial center of London, corresponds approximately to the Roman city as delineated by the Roman city wall, often referred to as the square mile or the financial district of London, because it's the sort of leading concentration today of financial sector activity in London. The medium black lines are the metropolitan boroughs that I mentioned, and then the light gray lines show these finely detailed parishes on which we have population data. And as you see, they really provide this sort of rich, high resolution information on economic activity going backwards in time. Just give you a sense of our transport network and how we've measured that over time. As I mentioned, the first passenger railway was in 1836. And so 1841 is the first population census year in which railways are present in the data. So here I've shown the area in white of the Greater London Authority again. The blue area is the County of London again, and the light grey shading is that historical City of London that I mentioned. And we've shown here the few railway lines that were present in this first census year of 1841. And what I'm going to do now is roll forward in time and show you the sort of expansion of the railway network over time. And then the black lines will correspond to overground railway lines, and the red lines as they appear will correspond to underground railway lines. As you can see here, in 1841, there were relatively few railway lines. They don't penetrate very far into the center of London for good reason. There was a lot of resistance to bulldozing central London and constructing railways through the very heart of London. And that was actually reflected in a parliamentary commission of 1846, which created an exclusion zone that excluded railways, overground railways from the very heart of London. And that was obviously part of the motivation later for the construction of the very first underground railway lines. So as we roll forward in time, you'll see this increasing density of railway lines crisscrossing the Greater London Authority area, until in 1871, we see the very first underground railway lines. The Metropolitan and District line was constructed in 1863 and began to take the transport network right into the very center of London. And as we roll further forward in time, you'll see this increasing intensification of the railway line, both the overground railway line network and the underground railway line, through to 1921 at the very end of our sample period. So quite a dramatic expansion in this new transport technology that permitted much higher travel speeds than pre-existing modes of transport. So even in the very early days of the railway, average travel speeds were around 21 miles an hour for overground railway lines, compared to around 6 miles an hour for the sort of pre-existing state-of-the-art transport technology, which were horse omnibuses at the very beginning of the 19th century. Obviously, when we look at the effect of the expansion of the railway network, we're going to want to control for that pre-existing transport network. And so we've collected and digitized historical maps on the horse omnibus and horse tram, and then later on electric tram networks over time. We're all paid members of the Omnibus Society of England and Wales, which very kindly made available historical maps to us that we digitized. And so here in 1839, you can see the historical horse omnibus network at that time, and then we've digitized those networks through to the very end of our sample period. So having kind of introduced the data, the sort of resolution at which we see this information, and the new transport technology, how it evolved over time, I'll sort of finish this first part of the talk by just trying to convince you something interesting happens in the data to explain and to try to think about with a quantitative model of the organization of economic activity within the Greater London area. So first piece of evidence we have here are some data on population over time. So what do we have here? Well, we've got two different panels. In the writer panel here, we've got the total population of the Greater London metropolitan area as a whole. It's expressed as an index number that's 1 in 1801, and then it shows in every subsequent year the proportional change in population relative to 1801. And so as you see here, by 1921, at the end of our sample period, we see this sort of more than 6-fold increase in the total population of the Greater London metropolitan area, a dramatic increase in total population as the metropolitan area expands over time. In contrast, over here in the left-hand panel, we see the total population of the historical heart of London. So this is the City of London, that Roman area, the very sort of commercial heart of economic activity in the London area. As you can see here, in the first part of the 19th century, total population in the City of London was approximately constant over time at around 130,000 people. And so that's sort of consistent with economic activity approaching some initial equilibrium density in the first half of the 19th century. And so the way the city grew over time was on the extensive margin. The area of developed land expanded outwards, the city got bigger geographically, and so that's how the metropolitan area was able to grow in population, even though the population at the very heart of that metropolitan area remained constant over time. Then from 1851, shortly after the invention of the steam passenger railway, we see this precipitous drop in residential population in the heart of the London area. It falls by around 90% towards the end of our sample period in 1921, a dramatic contrast with the growing metropolitan area as a whole, the sharp decline in residential populations at the very center of that metropolitan area. So, and I should just sort of flag here that this is not at all distinctive to London. You see exactly the same pattern in Paris. We sort of collected similar data for Paris. Also for Berlin, we collected the same data for Berlin, and even for US cities such as Boston, Chicago, New York. Again, you see this classic pattern where population density at the very heart of those cities starts to decline following the revolution in transport technologies during the 19th century. What might be going on? You know, is there a huge puzzle here? Well, we think that what's going on has a very natural explanation that is illustrated very starkly in this next figure here. And so what do we have in this figure? Well, again, we have the population in the city of London, the old Roman heart of London. That's shown here in black, the residential population, sometimes referred to as night population, approximately flat in the first half of the 19th century, then falls sharply from 1851 onwards. And here we've shown the population in thousands, around 130,000 at the beginning of the 19th century. And then the second line here in gray is what I referred to earlier as the day population from the City of London day censuses. So these recorded the number of people present during the day because the Corporation of London, the body that's responsible for the City of London, realized that the residential population in the population census was providing a highly misleading measure of how important the City of London was, because although night population, residential population was declining, the number of people present during the day was increasing dramatically. And so that's shown here in this gray time series here. And so what's going on, this makes a lot of sense. The City of London in the center of London was changing its pattern of specialization from a residential neighborhood where people lived and slept and stayed at night to a commercial area where people worked during the day and commuted to from the growing suburbs from the exterior parts of Greater London. And that's going to be something that our quantitative model predicts very sharply. It's going to have this key implication that when you have a revolution in transport technology that reduces the costs of separating where you live and where you work, what you should see is you should see locations start to specialize. Some places start to specialize as workplaces, namely the areas that have high productivity and are relatively productive and have an advantage as a workplace. And here, that's the City of London, the center of the London area. Other areas, such as the outer suburbs, where there's more space, can specialize as a residence where people live and enjoy the amenities of that space. Okay, so a first piece of evidence that what's going on here is this dramatic change in patterns of specialization that we are going to argue is closely related to the new transport technology. Another piece of evidence on what is going on, we show here the City of London, the old Roman hearts, share in the total value of all land and buildings in the Greater London area. And so what do you see here? How about this sort of share of value of land and buildings? Well, in the first half of the 19th century, the City of London's share is declining over time. That makes a lot of sense. Why? Because this is a share. And as we saw earlier, in the first half of the 19th century, the area of built up land in the London metropolitan area is growing as the city expands outwards. And so as the area of developed land gets bigger, the share of the already developed land in that total is going to get smaller because the denominator is increasing. So a very natural feature if the city is growing outwards on the extensive margin. However, in 1851, shortly after we see this sharp precipitous decline in population, we see that the City of London's share in the total value of all land and buildings in the Greater London area starts to increase. So that's important because it means that whatever is happening in the mid-19th century that's driving this change in pattern of specialization, residence population declining, the number of people present during the day increasing, it must be making the City of London relatively more valuable. It must be offsetting the secular decline in its share. And that's again going to be something that our model predicts, this new transport technology. It enables a separation of workplace and residence, and it's going to make the commercial heart of the metropolitan area relatively more valuable. And then a very final piece of evidence before I take a break. In the paper, we provide a lot of very detailed reduced form evidence that the arrival of the railway network, the precise timing of the arrival of the railway network, is very, very closely related to changes in patterns of population growth. I'm not going to spend too much time on that today because I think the area where I'd really like to try to build bridges between economics and urban planning and wider social sciences is really on our model and how we model and think about this new transport technology. But I'll just briefly flag that we kind of provide a lot of evidence trying to sort of tighten this connection between the arrival of the railway and changes in patterns of population growth. What's the main empirical challenge when we're making that connection? Well, obviously, the main empirical challenge is railway lines are not randomly placed. There's no kind of exogenous random variation in where people build railway networks, because you might deliberately choose to build a railway in a location where you expect economic activity to grow for other reasons. And so how do we address that non-random placement of the railway network in our empirical research? Well, we address it in several ways, one of which I'll explain later. But in the first part of the paper, we address it in a very simple, but I think quite powerful way, which is we're going to control for differences in trends of population growth across different parts of the Greater London area. So we're going to allow locations that get treated with a railway station to have a different trend rate of population growth from locations that are not treated with a railway station. We actually show in the paper that once you allow for those differences in trend rates of population growth, there's actually not a lot of other evidence of selection on other characteristics. And I'll just provide a very simple illustration of this now before I take a break. There's a lot more evidence in the paper. How do we control for those pre-existing trends? Well, a very, very simple way of doing that is what's often referred to as difference in difference estimator. So what are we going to do? How are we going to implement that? Well, for every parish in the Greater London area, we're going to compute a very simple difference in difference. So we're first going to look at a parish's population growth in the narrow window before a railway station is created. So we're going to focus on the 30-year period before a railway station is constructed in a location. And we're going to compute the rate of growth of population over that 30-year period. That's going to difference out any sort of unobserved location characteristic that affects the level of population in that location. So that's going to be our first difference. What's going to be our second difference? Well, we're going to look at the 30-year period after the arrival of the railway station, and we're going to compute another rate of population growth during that 30-year period after the arrival of the railway. Again, that's going to difference out any unobserved heterogeneity in the level of population in those locations, and that's going to be our second difference. And so what is the difference in difference? Well, we're just going to take the difference between those two 30-year population growth rates. In other words, we're going to look at the acceleration in population growth relative to its trend following the arrival of a railway station. And what do we see? Well, we see the results I showed you earlier for the City of London are not specific to the City of London. They're part of a broader pattern, which is illustrated in this figure here. What does this figure show? Well, it shows that acceleration in population growth, the difference between the 30-year period after the arrival of the railway and the 30-year period before the arrival of the railway. It shows it for every parish that gets treated with a railway station against that parish's distance from the Guildhall in the very center of the City of London, the commercial heart of the London metropolitan area. Parishes in the City of London that get treated with a railway station are shown by the red open circles. All other parishes outside the City of London are shown by the solid blue dots. And so here you see exactly that acceleration in population growth for every single parish. And then the black line here is a locally weighted linear least squares regression that just shows you how mean acceleration in population growth varies with distance from the center of the London metropolitan area. And you see the same pattern you saw earlier. Following the arrival of the railway, there's a slowing of population growth relative to its trend in the center, and an acceleration of population growth relative to its trend in the suburbs, consistent with the idea that the new transport technology enables people to separate where they live and where they work. But I should stop there now to sort of take a break and take some questions and discussion before moving into the model that's going to take up most of the rest of the talk. So it'd be great if there are any questions or any discussion at this stage.
Thank you, Steve, for this very clear introduction. I'm just going to say one technical thing. If you believe that your question is very difficult to type, you can just raise a hand, type the bottom, raise a hand, and we may try to put you live, or you asking the question at the next pause. Right now, we already have one question from Mike Batty, who says, Steve, that I'm going to read it because it's I don't want to lose any details. The population of the city was about 300,000 or even 400,000 in 1665. But during the talk, you said that at the beginning of the 19th century until 1841, the population of the city was stable at 130,000. So Mike Batty asked whether there has been a reason for the precipitous drop in the 18th century of the population, and whether this drop was due to the movement of population towards West End and Westminster. And is it possible that the drop in population is in the 19th century is seen as a continuation of the 18th century trends?
So great question. I think that figure of London's earlier population, there's a kind of debate when you start talking about the population of London as exactly what the definition of London is, and that turns out to sort of really be very consequential. So for the City of London, there's a question, do you include just the City of London within the walls, which is the sort of Roman part of the city, or do you also include the City of London outside the walls, which were parishes that were not officially part of the City of London, but over a very, very long period, including before the 16th century, had been very closely economically integrated with the City of London. And so I think that larger 300,000 figure would include not just the City of London, but the City of London without the walls, and also Westminster. And so I think one reason for the difference is that this figure of 130,000 here is I'm really focusing just on the historical City of London, not the surrounding areas which were part of the London area, but were not part of the, the area bounded by the Roman city walls. I mean, Mike, I think, knows much more about the history of London than I do, but he's also correct that there is a sort of another related point, which is that obviously the Great Fire of London was a very important part of London's history. And so there is some evidence that the population of even the area of London within the Roman walls was slightly less after the Great Fire than it was before the Great Fire. And so, there was that earlier historical experiment, which I do think is sort of important in thinking about the history of London. But at least our understanding is that, that the Great Fire was in 1666. There was a slight drop in population in that old Roman heart of the history of the historical area. But that the city had recovered some kind of historical equilibrium by the early 19th century, and that the situation was stable. There were many kind of decades when population is sort of stagnant. As a kind of check that, things are not really being affected by the Great Fire or any particular history of London, as I sort of mentioned, we have looked at other cities such as Paris, where you see a very, very similar pattern. So you see the Paris metropolitan area. Throughout the 19th century, you see the same pattern of growth. And then in the very heart of Paris, you again see this pattern where population starts to decline towards the second half of the 19th century with these new developments in transport technology. Obviously, there's a sort of slight difference in Paris, which is that in Paris, population in the historical center of the city. So these, I think, are the four arrondissements at the very heart of Paris. That was still growing in the early 19th century, which I think reflects the sort of different historical periods over which the two cities developed. And it may reflect the fact that in Paris, there wasn't an event similar to the Great Fire that I mentioned. But nonetheless, you still see this pattern of declining population following the transport improvements of the 19th century. You see exactly the same thing for Berlin. Again, even though these cities have really different histories, many different idiosyncrasies, you see the same pattern. And so I think the sort of idea that cities in the early 19th century were in some kind of equilibrium with the existing modes of transport, and then the invention of railways, which made this rapid long distance travel possible, the idea that that was kind of an external shock that perturbed and upset that initial equilibrium, I think that's a sort of a very generic feature. It's not sort of influenced by this sort of history of London. So sorry, that was a long answer. In short, I think there are 2 points. One is the sort of difference between the Roman wall and the area within that Roman wall versus the sort of larger settlement of London, which includes London without the walls, Westminster, other areas. And then the second point is an idiosyncrasy of London was the Great Fire, but that had sort of led to this sort of stable situation in the early 19th century. And then you have the shock following which population declines. So I hope that answers the question. I know Mike knows much more than I do about the history of London.
It seems to answer the question, and Mike also is saying that around 100,000 individuals died in the plague, and they also might account for the same loss in the mid-17th century. Not to take too much time out of your next section, I just would like to ask you to spend a few more words on the reasons why the transport network is endogenous, and what would be the role of private owners of the transport network and potential non-cooperative behavior.
Yep, so great question. I'll talk a little bit more about that when I get into the model. But I can dive in a little bit more detail into the reduced form evidence just briefly so as not to take up too much time. In the paper, we look at that sort of timing between the arrival of the station and changes in population growth in a much more detailed way. And the way economists do that is what's often referred to as an event study, where you look at an event, which is here, the opening of a railway station, and you compare places that get treated with the event to places that don't get treated with the event every year before and after the event. And so that allows you to see, leading up to the event, the places that subsequently get treated in the treatment year, do they differ even before the treatment to places that don't ever get a railway station? And then you can also look afterwards and see what happens. And obviously, as we were discussing, one of the key challenges there is that the places that receive a railway station might be different for other reasons. They might have higher population growth than places that don't get a railway station. Why is that? Well, because as Jamil just pointed out, that these railways are built by private sector companies who propose routes to Parliament that then had to pass an act to authorize those routes. And so obviously, if I'm a private sector company, I'm trying to maximize my shareholders' value, I'm probably going to try to pick places that I think are going to grow in population as places to build my railway. And so when you run this event study specification, if you don't control for the fact that locations that are treated with the railway and those that are not treated with the railway have different rates of population growth, then you find that even before the arrival of the railway, these two sets of locations look as if they have very different pre-trends in population. And so here is an example of that. Here's the event study. So time 0 is the year in which a place gets treated with a railway station. Positive years are years after the railway station. Negative years are years before the railway station. If you don't control for the fact that locations have different trend rates of population growth, irrespective of whether they get a railway station or not, you see what economists refer to as pre-trends, differences even before the event. But once you control for those differences in trend rates of population growth, you get this sort of beautiful event study picture. This is how event study pictures should look, where you see an acceleration of population growth after a railway station arrives, but no difference in pre-trends before the railway station is created. And so that's the reason why there might be these differences is the railway companies are private sector companies. And so that's why we allow for these differences in trend rates of population growth. So this is sort of on average for London as a whole. As I was highlighting earlier, there's also heterogeneity in different parts of London. The railway raises population growth in the center, decreases it, in the suburbs, decreases it in the center. We also see that in this event study specification, when you don't control for differences in trends, again, there are pre-trends, but they're negative in the center, measured here by the City of London. Once you control for those differences in trends, again, you get a beautiful event study picture where there are no differences before the arrival of the railway station, but in the center, a sharp decline in population growth afterwards. And so all of that sort of validates our idea that it's really the arrival of the railway that's leading to these changes in trend rates of population growth. Sorry, again, that was a long answer, but great question.
There was a very clear answer, and I think that now we can move to the model section in the interest of time, and we can take more questions later.
Great. And how much longer have I got? So I should stop about half an hour, or?
I think we're going to have another 25 minutes and then another stop and then again another.
Perfect. That sounds perfect. Okay, so let's dive into the model and how we're going to sort of think about this new transport technology conceptually. and then try to assess, can standard urban models really explain what's going on in the data? Can they be quantitatively successful? And so the model we're going to use is part of a class, as Jamil mentioned, of what are referred to as quantitative urban models in the economics literature that have become sort of popular within the last 5 years and are going to be become increasingly used in economics. In many ways, these models connect very closely to the kinds of frameworks that people have been using in the planning literature for many decades. And so you'll see that some elements of what I do today are going to be very similar to the kind of models people have been using in the planning literature and in other areas of transport economics and urban economics. So for example, the model I'm going to develop today is going to combine elements of a very standard random utility model that's been used for many decades in the transport economics literature. The thing that's sort of really new is the way in this quantitative spatial literature is the way that these random choice models are going to be embedded in a broader equilibrium structure. And so the key thing that's new is the random choice model is embedded in a whole model of economic activity within the entire metropolitan area. And so the whole goal is to sort of see how this new transport technology, it not only changes people's choices on individual routes, but it leads the equilibrium organization of economic activity within the city to change. And so essentially there'll be elements that are part of a random choice model and elements that are part of an older general equilibrium literature, which are really being kind of brought together here and then tried to use to understand this new transport technology. So how's the model going to work? It's going to be very, very simple. We're going to think about every worker in London choosing where to live. So workers are labeled here by omega, and they're geographically mobile. And what these workers do is they choose a place to live, a residence, N, and they choose a place to work, a workplace, I, out of some set of locations, which are our boroughs in the Greater London area. And what are workers trying to do? Well, workers are trying to maximize their utility. They're trying to make the best choice for them. And as in a standard random utility model, every worker is going to make the choice that's the best choice for them. So what does the worker's choice depend on? Well, it's going to depend upon the wage they can get at a particular workplace, I, and it's going to depend on their cost of living at a particular residence, N. What is their cost? So the wage here is W. What is the cost of living? Well, the cost of living is going to have two components, as in many economic models of cities. Those two components are firstly going to be the cost of the goods the worker consumes, the goods and services the worker consumes. Those here are labeled by P. So P is a consumption, goods and services price index, which is the cost of buying all the goods and services the worker consumes. The other component of the cost of living is labeled Q here, and that's the price of floor space. That's the price of living space in the house or apartment that the worker chooses to live in. And the alpha term here is just the weight of housing and goods and services consumption in the worker's consumption bundle. Okay, and so the worker looks for places that pay a high wage and that have a low cost of living. What else does the worker's choice depend on? Well, if the worker chooses to separate where she lives and where she works, she's going to face some commuting costs, kappa. And these are modeled here as an iceberg cost, a proportional cost that reduces your utility. And the longer the travel time you devote to commuting from where you live to travel to where you work, the lower your utility. And I've modeled here these commuting costs as being in terms of utility, but in the particular model I've written down, as you see here, utility is actually multiplicative in the wage. And so I could have, instead of equivalently modeled these commuting costs as being incurred in terms of time, the opportunity cost of time. If you're commuting, you can't be working and you can't be having leisure time. And then the final two elements of the worker's utility are going to be some common amenities, B, capital B here, which are specific to a particular residence, N, workplace, I pair. And they might be common things that make it more attractive to live in N and work in I. So what might that be? Well, maybe there's Hampstead Heath is in my residence. There's a sort of beautiful park in the residence, which makes it an attractive place to live. And maybe, the place where I work is in central London. It's very beautiful. It's again, an attractive place to work. And then finally, the key and crucial component of utility here is going to be the piece we take from random utility models. Every individual worker omega is going to have a random component of their utility, which I've labeled Z here. And that random component is specific to a particular residence workplace pair. So how should I think about this? Every worker gets a random draw for every possible residence workplace pair. There's a whole matrix of residences and workplaces, and the worker gets an idiosyncratic draw for how attractive she finds that particular pair of residence and workplace. And so what's the economic idea here? Well, as we all know, there are many idiosyncratic factors that affect where I live and where I work. You know, maybe my mother lives in this neighborhood and I want to be near where my mother lives. Maybe my uncle or my aunt owns a factory in this other neighborhood and they offer me a job, and so I end up working there. There are all these idiosyncratic things which no model can hope to capture. And so those are captured with this random shock to individuals' utility. It's going to lead different workers to make different choices, even given the same economic variables. And so building on that older random utility literature, we're going to assume that this random component of utility, Z, is drawn from an extreme value. And the extreme value distribution here, G, this is a probability density function. Oh, sorry, it's a cumulative distribution function. G here is a CDF. It's an extreme value distribution. The particular type of extreme value distribution we've assumed is called a type 2 extreme value distribution, also referred to as a Frechet distribution. Those of you who've worked with random utility models in the planning literature, you probably more frequently work with type 1 extreme value distributions or Gumbel distributions, as in the conventional logit model in the transportation literature. It's not particularly important that this is a type 2 rather than a type 1 random utility model. The only reason for that distinction is the type 2 model I'm using works very well when you have a model that's multiplicative, which is the particular model I have here, whereas a type 1 extreme value distribution works very well when you have a model that's additive. Otherwise, they're essentially isomorphic. But that's just to sort of emphasize the connections with models that people may be more familiar with. So why have I set up the worker's utility in this way? Well, I want to capture this intuitive idea that people care about the wage where they work and the cost of living where they live and the amenities where they live. Why have I assumed the extreme value? Well, it's going to have this beautiful property that's going to make a lot of sense when we go to the data. What does this extreme value distribution predict? Well, it yields a very, very simple but powerful prediction. It predicts that commuting flows between locations follow a gravity equation. Why is that useful? Because when you look in the data, you find that gravity is an extremely powerful property of the data, as I'm going to show you later. And so in particular, this is what the gravity equation is. What does the gravity equation mean? It means that the probability lambda a worker chooses to commute from a residence N to a workplace I, it depends upon characteristics of the workplace. So it's like Newtonian gravity. You know, planets attract one another. They attract one another depending upon their mass, the mass of each planet. Well, the mass of the planet here is the attractiveness of the workplace, the wage, and the attractiveness of the residence, the cost of living in that particular residence. So that's the kind of part of Newtonian gravity, the mass of the two planets. What's the other part of Newtonian gravity? Well, the attraction of those two planets is inversely proportional to how far apart they are, the distance between them. What's the analogy here in the commuting model? Well, that's the commuting costs. They play the role of distance in the sort of Newtonian gravitation analogy. Okay, so that's an implication of this particular model, and it's a really, really strong feature of the data. So arguably any sensible model you write down and take to the data has got to confront that property of the data, that, you know, big locations have more commuters between them, and locations that have low travel times between them have more commuters. Another feature of this particular extreme value distribution that turns out to be really useful if you want to put this random utility model inside a general equilibrium model is that in equilibrium, the expected utility from picking any particular workplace and residence pair in the metropolitan area of London turns out to be the same across all possible choices you can make, and equal to workers' outside option, which is to go and live in the larger economy of England and Wales. So that's useful because it means that we can have an equilibrium where people are thinking about living in London or living elsewhere. And so we can think about the change in the size of London as a whole over time. And it's also useful because in equilibrium, every pair is going to offer the same expected utility equal to the outside option. And so you're probably thinking that's very puzzling, because aren't some commutes more attractive than others? And shouldn't they give you higher utility? Well, that intuition is exactly right. The reason the average utility is not different is because the commutes that are more attractive, they attract commuters with lower idiosyncratic draws, precisely because they're more attractive. And so there's a composition effect. Better commutes attract workers with lower idiosyncratic draws. And so on average, once you take into account the idiosyncratic draw, the mean expected utility turns out under this extreme value distribution to be the same across all choices, which enables us to have an equilibrium model where people are thinking about living in London or the wider economy. And then in the paper, we actually outlined that this is not a single model. We can actually capture a whole class of models in the economics literature in much of what we do. And so we think that many of our conclusions are going to be robust across that entire class of models. But before we take our next break, let me show you how we can actually take this model directly to the data and how we can use it to think about the experiment of building a railway network in Greater London. So an advantage of the approach is we're just going to have this sequence of steps where each step is going to involve a minimal additional assumptions. So in the first step, we're just going to take our commuting data at the very end of our sample period in 1921, which is something we directly observe, the flow of people from every residence N to every workplace I. Using those flows, we can calculate the measure of residence, the number of people who live in every residence. So R is the number of residents. And we can also calculate the number of workers, L. That's the number of people who work in every location in the London metropolitan area. We can also calculate commuting probabilities, lambda, and this is actually a conditional commuting probability. That's what the C means. Why is it a conditional commuting probability? Because it's the probability conditional on living in residence N that I choose to commute to workplace I. And that's going to be a particularly useful commuting probability to work with in the model. So that's the first step. It's just trivial. You just add things up in the data. What's the second step? Well, we want our model to be in equilibrium in 1921 at the end of our sample period. And then we want to think about what would happen if you remove the railway network, and how would economic activity reorganize in London, and can the model capture what actually happened in the data. So we're going to need an equilibrium condition to make sure the model is in equilibrium in 1921. What's that equilibrium condition? Well, it takes a very simple form in our model. The income of people who own land and buildings, which is something we directly observe in our data, with what are termed rateable values, that has to equal in the model, the income of the people who own the land and buildings has to equal payments for the use of those land and buildings. So how are they used in the model? Well, they're used for production in commercial uses, and they're used for residence in residential uses. In the particular model I wrote down, it has a very kind of convenient property which enables us to do our analysis, which is that payments for the commercial use of floor space are proportional to income by workplace, which is just the number of people who work in every location and the wages they're paid. And residential use of floor space turns out to be proportional to the income of residents, which is the number of people who live in every location times their average income. And what is people's average income inside this model? Well, that's just the wage in every workplace multiplied by the probability you commute to that workplace from this particular residence. And so in our initial year in 1921, we see in the data the number of people who live in every place R and the number of people who work in every place L. We also see these commuting probabilities, lambda, and we see the value of land and buildings, income from the ownership of land and buildings. The only thing we actually don't see in our data is the wage, because wage data were not reported for London at that level of detail. And so what we do is we use the model to solve for what the model implies the required wage should be. And then in principle, if you have separate data on the wage, you can check that implication. And so we just solve this equation for the wage, and then the model's in an equilibrium in 1921. And then the real thing we're interested in is, what does the railway network do to the structure of economic activity? And that's the whole punch in the paper. And so how do we do that? Well, we're going to use the following methodology. We're going to estimate the effect of railways on commuting costs just using this bilateral commuting data we have in 1921. So all of our estimation is only going to use information in 1921. And then we're going to remove the railway network, recalculate what commuting costs would be if you just delete the railways, and then use the model to predict what happens going backwards in time. So how do we estimate commuting costs? Well, we use an approach that's very popular now in quantitative spatial economics. We're going to take the area of Greater London and we're going to discretize it into millions of grid points, a grid of millions of points that we plot down onto the space of the Greater London metropolitan area. On top of all those millions of points, we're going to overlay maps of the transport network that show us where the railway lines were, the overground railway lines, the underground railway lines, omnibuses and trams. If a point has is on top of a railway line, we're going to say that the cost of traveling over that point is going to be proportional to the speed at which you can travel by railway. If a point on this grid lies on top of an omnibus or a tram route, we're going to say that the speed at which you can travel over that point is equal to the speed of omnibuses and tram routes. How are we going to pick those speeds for the different modes of transport? Well, we're going to base them on historical data that London County Council collected and reported, where it measures overground railways as traveling at around 21 miles an hour, underground at 15 miles an hour, omnibuses and trams at around 6 miles an hour. And then if there's no omnibus and tram route, we assume you have to walk, and we're going to assume an average travel speed of 3 miles an hour. And so we'll just normalize the costs for overground railways to 1 and set the costs for the other modes as proportional to their relative travel speeds. And then if a worker wants to travel from where they live to where they work, what they're going to do is they're going to follow the least cost path. They're going to travel over these millions of points on the surface of Greater London, and they're going to choose their path across those points to pick the path that has the lowest cost. And so they're going to optimally switch between modes of transport, between walking, omnibuses, and railways. And we assume you can only join the railway network at a place where there is a railway station, and we assume a 3-minute penalty when you change modes of transport. And so once we've got those weights and we know where the network is, we can calculate bilateral commuting times in 1921. And so the only thing we have to do is we have to estimate the relationship between commuting flows and commuting costs. How do we do that? Well, we do that with this, what's referred to as a gravity equation in the economics and transportation literature. We're going to regress the number of people who commute between residence N and workplace I in 1921 in the bilateral data we observe. We're going to regress the log of that on a workplace fixed effect, which in the model captures wages, things that make workplaces more attractive. A residence fixed effect, which in the model captures the cost of living, things that make a residence more attractive. And then we've got the log of our travel times that we've computed using these weights up here. And then there's an error term, which is all the idiosyncratic factors that affect commuting costs that our model doesn't capture. And the only thing we have to estimate here is this composite elasticity, epsilon times phi, which captures 2 things in the model. It's the elasticity of commuting costs to travel times and the elasticity of commuting flows to commuting costs. That's why it's a composite elasticity. But we can just estimate that composite from this regression. And again, to deal with the fact that the transport network is potentially endogenous, we instrument travel times using the railway network, using straight line distance as an instrument. And then that gives us this estimate of this elasticity, epsilon phi. And so, one concern you might have is this is obviously a very simple model of commuting modes. We're just assuming travel time is the only thing that matters. We're not taking into account the price or the cost of using these different modes of transport, how pleasant it is to sit in a train versus sit on an omnibus, etc. All these many things we're abstracting from. But nonetheless, we find that this pretty simple model seems to do a pretty good job in predicting the cross-sectional pattern of commuting flows in 1921. So what this figure does is it graphs the log of commuting flows after removing the workplace and residence fixed effects against the log of commuting costs after removing the workplace and residence fixed effects. Our model says this should be log linear, and it appears to be approximately log linear. Our model's obviously not perfect. The model says commuting costs should lie along the red straight line, and they're obviously not exactly on that red straight line, but they appear to be relatively tightly clustered around that line. And so we sort of take this as evidence that although our model is necessarily an abstraction, it seems to do a reasonable job at approximating the pattern of commuting costs in 1921. And then the whole action now is we're going to go back in time. We're going to take this estimated parameter for 1921, hold it fixed, And the only thing we're going to do is we're going to remove railway lines going all the way back to the early 19th century. And we're just going to recalculate commuting costs once we remove the railway lines. And that's going to give us a prediction for the change in commuting costs. We're going to feed that prediction into the model and use the model to predict how will people relocate given those new commuting costs. How do we do that? Well, we use a method that's called exact hat algebra in economics. I think it's actually very wide applicability in urban models. So I think it's sort of very powerful technique that could be more widely used. So how does it work? Well, in 1921, we see everything and the model is in equilibrium, apart from the wages we solved for earlier. The model is in equilibrium in 1921. We want to predict things going back in time. And so I'm going to label every earlier year tau, that's before 1921, that's earlier. And I want to make a prediction back to year tau. How this exact hat algebra works is I'm going to take my equilibrium condition in year tau, which says that the income of landlords has to equal payments for residential and commercial floor space. Now, I can't really do anything with that equilibrium condition in year tau. Why? Because I don't observe some of the things that I would need to observe in the earlier year in the 19th century. In particular, I don't observe employment by workplace in the 19th century. And so you'd sort of think it would be hopeless to use the model because you don't observe the things you would need. But this exact hat algebra approach is going to solve that problem for us. Why? Because I'm going to rewrite my equilibrium condition in the earlier year in the 19th century. On the left-hand side, I've got the income of landlords. I'm going to rewrite the income of landlords in, for example, 1851 as equal to the income of landlords in 1921, which I do observe, times the ratio of the income of landlords in 1921 to 1951. Okay, and so the hat here, the exact hat, it just means the ratio of a variable in year tau divided by the value of the variable in year t. And this is obviously just an accounting identity. If I take a variable in year t and I multiply it by the hat of that variable, I'm multiplying xt by x tau divided by xt. The xt's cancel and I get x tau back. And so this is just an accounting identity. I'm just rewriting the equilibrium condition. On the left-hand side, I actually observe both the value in 1921 and the ratio going back to the 19th century. And so it's really just rewriting things in a more convenient form. But on the right-hand side, there are some things I don't observe going back to the 19th century. In particular, I don't observe the relative change in wages and employment by workplace back to the 19th century. And so that's the whole power of this approach. I'm eliminating the W tau, which I don't see, and I'm replacing it with a WT, the wage in 1921, which I solved for earlier, and a relative change, which is here. The relative change in the wage is going to be the only thing I don't observe. And I'm going to rewrite employment in 1851, which I don't observe, in terms of residence in 1921, the relative change in residence, and patterns of commuting. And by essentially playing with this equilibrium condition in 1851, just by being smart about how I rewrite that equilibrium condition, I can rewrite it in terms of things I observe, which are either in 1921 or their relative changes back to the 19th century, which I do see in my data, namely population and the value of land and buildings. And I'm going to eliminate everything that I don't see, namely the relative change in wage and the relative change in employment. And in fact, if I keep playing long enough, I can reduce the entire equation down to there being only one thing I don't observe, which is the relative change in the wage. And so I'm just going to start in, effectively, I'm starting in 1921. I'm feeding in the observed changes in the value of land and buildings and population. And I'm feeding in my estimated changes in commuting costs. And then the only thing I've got left, which I don't see, is the change in wages back to the 19th century. And so I'm just using this equation to solve for those changes in wages. Why is that useful? Because once I've solved for the change in wages, the model predicts what happens to employment by workplace going back into the 19th century. And in fact, it spits out commuting flows for every year going back to the early decades of the 19th century. So before we take our next break, I want to kind of stop by saying, well, that's all well and good, but how well does the model work? To what extent is this model successful at understanding how economic activity reallocates following the removal of the railway? And so that's the thing I'm going to end with before this break. So I'm going to return to my data on the City of London. In gray here, we've got the data on residence population that we saw earlier, around 130,000 in the early decades of the 19th century, and then it falls precipitously. The solid black line here is the data from the day census that you saw earlier on the number of people present during the day, which we're going to interpret as workplace employment in terms of the model. And then the dashed black line here are the model's predictions for employment by workplace going back every decade into the 19th century. Very important feature about the model and a very key strength of this whole approach is I'm conditioning on the observed population here, going back every year into the 19th century. So by construction, the model will exactly replicate those data. Why? Because I'm conditioning on them here. I'm rewriting this equilibrium condition in terms of the observed populations and the observed land values. That's really, really important because inside the model, that enables me to control for changes in productivity, changes in amenities, such as the health environment, changes in the costs of trading goods, changes in the outside option of working in the rest of England and Wales, which plausibly changed going back to the early 19th century. Because I condition on those observed variables, I'm able to control for everything else that changed and focus on purely what was the effect of the railway on commuting costs. But obviously there's no surprise that the model exactly matches the observed population because I set it up in that way. I've also set the model up so it exactly matches workplace employment in 1921. So it's exactly correct in 1921. So obviously the only information content in this figure is how well the model does in years before 1921. And it's not perfect, but nonetheless, you see the model is kind of strikingly successful in capturing this sort of secular separation of employment by workplace and employment by residence. And the model implies, if you go back to the early decades of the 19th century, the City of London did have some net inward commuting. So employment by workplace exceeds employment by residence in the City of London, but it was relatively small, consistent with the idea that at the dawn of the railway age, most people lived close to where they worked. Is there any other data we could use as a check on the model's predictions? Well, another piece of data we use is we managed to get the personnel records of the Queen's tailor, who are Henry Poole Bespoke Tailors, which have been located on Savile Row in Westminster since 1821. And so the advantage of that company for our purposes, it's been around a long time, and they actually kept personnel records that recorded the residence address of everybody who worked in the company. And so obviously we know where they work because Henry Poole have been at the same place on Savile Row. And we have the personnel records that say where they live. And so what we do is we look in the data in Henry Poole's personnel records in the years surrounding 1861. We look at a window either side of that. And we look, we geolocated the residence addresses that are written in the ledgers of the company. And then we looked in the data what fraction of Henry Poole's workers commuted different distances in 1861. And so we find around 90% of the workers commute less than 5 kilometers, consistent with the idea that indeed most people live close to where they worked at the dawn of the railway age. And very few people commute longer than 5 kilometers. And then in light gray here, we've compared that with the model's predictions for the borough of Westminster. Obviously, again, the model's an abstraction. It's yielding a prediction for all of Westminster rather than this particular address where Henry Poole are located. But nonetheless, the model seems strikingly successful in capturing the idea that most people commute less than 5 kilometers at the dawn of the railway age. And then if you do the same thing for 1901, again, comparing the model's predictions with the personnel records, again, the model's not perfect. In light gray here, it doesn't line up perfectly with the data in black, but you know, this is just one employer in one particular address. But nonetheless, it captures this sort of key feature of the data, which is that by 1901, by the turn of the 20th century, many people are commuting over distances up to 20 kilometers. Why? Because the dramatically faster travel times that the railway makes possible enable people to do that. And inside the model, there's this welfare gain to separating where you live and where you work. So just an example of how we can take the model to the data, use it to predict what would have happened to commuting patterns if you eliminated the railway, and how we can actually confront the model with the data. And I think I should take another break there to take many questions. I'm sure there are a number of questions about the model, and it'd be terrific to have a discussion now.
Yes, thank you, Steve, for this theoretical tour de force. It is extremely challenging to condense such a complex model in a few minutes. In terms of technical management of time, I would like to reserve a few minutes at the end for the discussion of a few elements that have come out during the talk, in particular the role of landowners and land profit extraction. Briefly, I will try to summarize some of the elements that you have discussed. First of all, thank you for pointing out the similarities between the use of Gamble and Fréchet distribution, which is definitely a bridge between the literatures in urban modeling and transport versus the usual economics approach. So I would like to stress the fact that the probability of commuting is the result of a tension between bilateral resistance on the nominator and multilateral resistance on the denominator. So it's something that is very similar to a multinomial logic model.
Mm-hmm.
Then for the audience that is maybe less familiar with the gravity equation modeling, I would like to ask you to spend maybe a few words on the similarities and dissimilarities between the trade literature and the internal city structure literature, and in particular on the fact that usually the trade literature uses and urban literature uses a semi-log specification, while in this paper you use the log-log specification. Is there a particular technical reason?
Yeah, these are all great questions. So just say a little bit more about the gravity equation. I think it's sort of it's been really important in urban economics because before this approach to modeling things, economists did have models of cities, but they're very, very hard to solve in a realistic setting, such as the setting you have here, where you have many locations which are different from one another in their transport networks and so on. It was very, very hard for economists to solve those kind of models. And so they had to make extreme assumptions, like the city lies along a line, it's a one-dimensional city, or the city is in a perfectly symmetrical circle, which is very insightful theoretically, but it's obviously hopeless when you go to the data. And so one very, very key feature in everything we're doing is this gravity equation that you're pointing out. And you correctly pointed out this gravity equation for commuting flows is very closely related to the gravity equation in international trade flows. And it's actually interesting as an economist, for a long while, people had looked in the data for trade and for commuting, and they find this sort of gravity property that if two locations are big, they attract more interactions, whether that's flows of people or whether it's flows of goods. If two locations are close together, they also attract more interactions, whether it's flows of people, whether it's flows of goods. And for a long while, we actually didn't have good theories that would explain where that relationship came from. And so people just appealed to Newtonian gravitation and thought of this as a purely an empirical model. But now we actually have a number of micro-founded theoretical models which give this property. And this is an example for commuting flows, where if you have extreme value idiosyncratic preferences, as in the logic model you mentioned, it gives you this gravity model in commuting. One very kind of key feature, and Jamil mentioned it a moment ago, he mentioned this distinction between bilateral resistance and multilateral resistance. What does he mean by that? And again, I'm sure you're familiar with that in the planning literature and the transport literature. The bilateral resistances are the bilateral travel costs. The number of people who commute from residence N to workplace I, that depends upon how long it takes you to commute between residence N and workplace I. But a key insight of these, of a multinomial logic model, is that the number of people who make that choice doesn't just depend upon how attractive that choice is, it depends on how attractive all the other choices are. And so that's the multilateral resistance here. The bilateral commuting costs for every other possible choice you can make, which show up here in the denominator. And the general equilibrium element of the model is implicitly when I do these what are called counterfactuals, when I feed in these changes in commuting costs, in the background, there's a whole general equilibrium problem that's resolving for this multilateral resistance. And it's taking account that when I change the commuting costs, I'm not just changing the bilateral commuting costs, I'm changing the attractiveness of every other pair. And when I read that equilibrium condition earlier, it's all of that those general equilibrium adjustments they're being captured in the observed land values and the observed populations. But later on, when I do an out of sample prediction, when I make a prediction for something that hasn't happened yet, I'm going to have to solve for all of those general equilibrium effects, those changes in multilateral resistance. And so it's a great point, Jamil, to highlight that and emphasize that.
Thank you, Steve, for this very clear explanation. Before moving to the next section, I would like to ask a final question, which is, in the model, you assume that workers are ex ante homogeneous and they become ex post heterogeneous in the idiosyncratic shock in their amenities preferences, or seen as effective unit of labor. I would like to ask you, what is your take on the possibility of ex ante heterogeneity of workers, so either in skills or occupation?
Yeah, that's another great question. In this paper, we treat all workers as being ex ante the same, as you pointed out. I mean, the main reason for that is just data availability. The data that are available back to the early 19th century are very limited. And as you can see, even with a single type of worker, we've really had to use the model to fill in some pieces of the data we don't observe. And we think that's actually one of the key contributions of what we're trying to do in the paper. And so the only reason for focusing on a single type of commuter is partly the limitations of the data. I think there is also another kind of good economic justification for that, which is that there's a lot of evidence that this idea that before the railway, it was very difficult to separate where people live and where they work. There's a lot of evidence that that was true for workers across many different types of occupations. So it wasn't just true for the rich, it was also true for the poor and for the middle class. That you know, obviously there were some exceptions, but in general, most people lived close to where they worked. And in the paper, we actually provide some evidence supporting that using the, for Philadelphia, there's a project where people have gone back in time and they've commuted travel distances for people in different occupations. And we show that those travel differences increase over time with transport improvements across a broad range of occupations. We also use the historical data on where people live by residence back in time. And we show that the average distance of pretty much all occupations from the center of London increases over time. That's, you know, partly natural because London's expanding outwards, but it highlights that it was not just the rich that fled to the suburbs, that there were middle class, working class suburbs. That was partly facilitated in London by what were called working men's trains. From 1860 onwards, Parliament forced railway companies to provide working men's trains. And then in 1881, there was actually explicitly a Working Men's Trains Act. But that's, so I think it's actually kind of plausible based on that evidence that, you know, the first order effect of the railway was it made it easy for everybody to commute. It was previously very, very costly, prohibitively costly for nearly everybody to separate where they lived and where they worked. Now, of course, that's not to say that the effect of the railway was identical across all the occupations. And in fact, a really interesting area in quantitative spatial economics is thinking about having multiple types of workers that might systematically sort across different types of neighborhoods. And I actually have another project where we're working on that, where we're using, as many of you may be familiar with, the data of Charles Booth on socioeconomic status in London. We're working with the Booth data back to the 1890s and using wartime destruction as an exogenous shock to locations and trying to look at patterns of spatial sorting in a model similar to this model where you have many different types of workers. And so these methods can absolutely be extended. We think for this application, it's sort of reasonable to think that the railway, you know, dramatically reduce commuting costs for all types of workers. And in any case, the data limit to, you know, what we can do back to the early 19th century. But it's a great point, great question.
Thank you. This was a very clear answer. I believe we can now move to the final section of the presentation, which will last around 20 minutes, so we can leave around 10 minutes for discussion. Thank you.
Great, thank you, Jamil. So we've now sort of validated this approach by showing that the model is able to kind of capture this large-scale separation of workplace and residence and match historical commuting patterns. One implication of that, of course, is we can back out from the model the entire distribution of workplace employment across locations. And so this shows you those distributions. So in 1921, which is shown by the black lines, this is just log workplace employment divided by land area, log residence employment divided by land area in 1921 for every borough in our data, graphed against distance to the Guildhall in the center of the City of London. And so this is showing employment density by workplace and by residence. And 1921, that's just data. And I've just fit an average curve through that data, again, using a locally weighted linearly squares regression. In gray here, you see the same objects in 1931. Employment by residence in 1831, employment by residence in 1831, that's essentially data. We get that from the population data. But employment by workplace in 1831, that's a model prediction. That's something the model's filled in for us, the missing data. And as you can see, consistent with the other evidence we've seen in 1831, workplace and residence employment density are pretty much on top of one another. And by contrast, in 1921, you see that the central parts of London become net importers of commuters because employment workplace is greater than employment residence, whereas the suburbs become net exporters of commuters. And that lies behind the effects of removing the railway network as you go back in time. Once you move the railways, it becomes very difficult to commute between locations. And so you're unable to export commuters from the suburbs and import them into the center. What else can we do within the model? Well, we can do a bunch of stuff. The most exciting stuff I want to show you are the counterfactuals for where we can make outer sample predictions, because that can be very useful. For example, in a present day setting where you wanted to predict Crossrail, what will be the effects of Crossrail on economic activity in London, or what will be the effects of HS2 for economic activity in England and Wales as a whole. But before we get to those counterfactuals, I'll illustrate something else we do with the model, which is recover implied productivity and amenities for every location in London. And we use the model to estimate the strength of agglomeration economies. So as I said earlier, the sort of baseline approach we've used here to reconstruct employment by workplace and commuting patterns back to the early 19th century, its key strength is it uses population and the value of land and buildings to control for many other things that changed, for productivity and amenities and so on. And it actually holds in a whole class of urban models. When we want to recover productivity and amenities and estimate the strength of agglomeration economies, in this next part of the talk, we do need to impose a little bit of extra structure. And so we have to make some stronger assumptions here. And so I'll just flag that to you before I show you the model's implications for productivity and amenities. So for example, we have to assume that workers' goods consumption, it now consists of just two goods, a freely traded consumption good, which can be traded freely within Greater London. And there may be trade costs with the rest of the economy, but there are no trade costs within Greater London. And then there's a good that's entirely non-traded, so services that can only be locally traded. And those two goods are produced using labor and floor space according to what's called a constant returns to scale technology. What does that mean? It means if you double the amount of labor and floor space you use, you double the amount of output you generate. And so that's the extra structure we need to recover productivity and amenities. Final piece of extra structure. Feature of our data for England and Wales is we see what are called rateable values, which are the value of land and buildings. Because they're the value of land and buildings, it's actually the price times the quantity of floor space. That's the thing we observe in the data. And that was very useful earlier when we were using the model to predict what would be the effect of removing the railway network. But now we want to recover productivity and amenities. We need to be able to separate the price and the supply of floor space. And so again, we need some extra structure. Where do we get that from? Well, in the economics literature, particularly here in the US, there's a very influential paper by Albert Seiss in 2010, which argues that there is approximately a constant elasticity supply of floor space. In other words, the supply of floor space that's built in a location depends on its land area and is a constant elasticity function of the price of floor space. So as the price of floor space goes up, you construct more floor space. So obviously that's an extreme simplification, but he argues that it fits the data quite well, and so we adopt his assumption. And so we split up the price of floor space, which you'll remember was called earlier Q, this non-script Q. The script Q here are our rateable values, the value of the land and property that we see directly in the data. And then we're going to use H to denote the quantity of floor space. So Q here is the price of floor space, H is the quantity of floor space. Under this Seiss assumption that the supply of floor space is a constant elasticity function of the price of floor space, we can actually separate our rateable values into the price of floor space and the supply of floor space, and they're both just constant elasticity functions of rateable values per unit land area. So K here is the unit of land area. Another way of microfounding this is to have a construction sector that uses capital and land to produce buildings. That will also deliver this relationship. And so we use that assumption to separate the price and supply of floor space. Once we do that, inside of our model, we can recover the implied productivity of every location, which is called A here, and we can recover the implied changes in amenities that are implied by the observed changes in population and the observed changes in the value of land and buildings that we see in the data. What do those look like? Well, they exhibit intuitive properties in the data for the London metropolitan area. So in the top left panel here, we're showing the log of rateable value per unit land area, which is going to be proportional to both the price and the quantity of floor space. And again, I'm graphing log rateable value per land area against distance from the Guildhall here. The black values are 1921 values. The grey plot are the 1831 values. And you see a very familiar pattern. You see that the gradient in rateable values gets shallower over time as the area of developed land in London expands outwards. That gradient gets shallower, so this line is less steeply sloped. You see the largest proportional increase in rateable values in the inner suburbs of inner London, so the sort of Wandsworths, Battersea, Kensingtons, Chelseas. They're the areas that see the biggest proportional growth in rateable values over our sample period. When we look at the growth in productivity, that's in the top right panel here. So productivity is here expressed relative to productivity in the City of London. We find that the innermost parts of the London area see their productivity rise relative to the outermost parts. And that's seen here by productivity relative to the City of London is comparatively similar in both 1831 and 1921. But in 1831, the outer suburbs of London have much higher productivity relative to the inner parts of London. In other words, in 1921, the suburbs are less productive relative to the inner parts. And so that's consistent with the idea there was greater productivity growth in the center as economic activity reorganized and specialized by workplace and residence. How about amenity growth? Well, this greater proportional growth in rateable values in the inner suburbs is partly explained in the model by improvements in commuting access. It's easier to commute from, say, Battersea or Wandsworth into the City of London in the area of the railway than it would be without the railway. And that makes the suburbs more attractive. And so there's an improvement in commuting market access. And in the model, that increases their population. But the growth in population we see in the data is too big to be fully explained by the improvement in commuting market access in the model. And so the way the model explains that is it explains it in terms of changes in amenities. In other words, these changes in amenities are being backed out as a residual that rationalizes the observed data as an equilibrium of the model. And so this is consistent with the idea that as you build houses in Battersea and Wandsworth, you also build public libraries, you build roads, you build parks, you build other amenities to make those places more attractive locations to live. And so we see both increases in productivity, but particularly concentrated in the inner areas of London, and increases in amenities, particularly concentrated in sort of intermediate inner suburbs relative to outer suburbs. What we do in the paper, I'm short on time, so I won't spend too much time on this, is we use those implied changes in productivity and amenities to estimate the strength of agglomeration forces. So there's a big literature in economics which says both productivity and amenities should be related to the density of economic activity. As you concentrate employment in a location, that increases employment density, that should increase productivity by, for example, increased knowledge spillovers. So there's a huge literature in economics trying to estimate that. It's very, very difficult to do. Why? Because there's an obvious causality problem. So what's the causality problem? Well, if you regress productivity in A here on the left-hand side on employment density L on the right-hand side, or you regress amenities on the left-hand side on residence density on the right-hand side, there's a clear endogeneity problem or causality problem. So on the one hand, if you increase density, that could cause higher productivity. On the other hand, if you increase productivity, that could cause higher employment density. Clearly, there is two-way causality between the two of those variables. And so in my work, I've tried to address that endogeneity problem in a couple of ways. I've got a paper on the Berlin Wall where we try to use the Berlin Wall as an exogenous shock to identify the strength of agglomeration economies. Here we use the reorganization of economic activity in London with the steam railway as a natural experiment that identifies these agglomeration economies. And so formally, the way that shows up here is we estimate these parameters using what's referred to as the generalized method of moments by requiring that the unobserved component of productivity and amenities is orthogonal to distance from central London. Once we control for the model's economic forces of changes in commuting market access for both residents and employers. So it says that when the railway improves travel times, that improves commuting market access, it induces changes in employment density and residence density. There can be some effect of that on productivity and amenities, but the idiosyncratic shocks to productivities and amenities have to be orthogonal to location within the greater metropolitan area, distance from the Guildhall. Under the identifying assumption, which admittedly is a strong assumption, comes with the usual caveats, but we find elasticities of productivity density of around 8%, which are actually pretty close to what we found for the Berlin Wall and what other people have found using other instrumental variable estimation strategies. And they're substantially smaller than what you would find if you don't control for the endogeneity problem. We also find endogenous amenities, which is a sort of common finding in economics as well. Again, we obtain, once we instrument, we get numbers which are pretty in the line of what other people have found and are much smaller than when you don't control for the endogeneity problem. What I want to spend my last 8 minutes on is kind of illustrating to you how this framework not only can be used to kind of go back in time and generate missing data and estimate the strength of agglomeration forces, which is what I've done so far, but it can be used to think about counterfactual questions. Okay, and so these counterfactual questions are sort of very different from the exercise we went through earlier. Why? Because in the exercise earlier, I was removing the railway network, conditioning on the value of land and buildings and conditioning on population. That was a real strength of the earlier approach because it enabled us to isolate the effect of changes in commuting costs while controlling for changes in productivity and amenities. But now I want to ask a counterfactual question. I want to say, what would have happened in London if the only thing that changed was the change in commuting costs and productivity and amenities didn't change at all? And that's a counterfactual question because obviously in reality, productivity and amenities did change. But what I'm interested in now is the pure welfare effects of the change in transport infrastructure. And that's a very interesting question to ask because obviously in other settings, when I'm thinking about Crossrail or HS2, I'm also interested exactly in that question of what is the pure welfare effect of changing the transport network in this way. And so I want to illustrate how these methods are very powerful and can be used to think about those counterfactual questions. Furthermore, you can not only do just one counterfactual, but you can do a whole menu of counterfactuals where you see exactly how your results depend upon alternative assumptions you make about things such as the supply of floor space, how the built environment changes when you build the new transport infrastructure, or assumptions about the strength of agglomeration economies, whether there are any agglomeration economies at all, whether productivity and amenities are in contrast exogenous. And so as we'll see, it's very easy to implement these counterfactuals under lots of alternative assumptions. So we're going to report 3 sets of counterfactuals. We'll remove the entire railway network, going back to the early decades of the 19th century. We'll remove just the railway network, and we'll remove the railway lines constructed in the very final decade of our sample to look whether there were sort of diminishing returns to expanding the railway network over time. As I kind of highlighted, we'll undertake these counterfactuals under a range of assumptions about other model parameters, such as whether floor space responds endogenously or whether there are agglomeration forces. And when we do these counterfactuals, we'll allow for migration between London and the rest of the economy at a rate determined by one of the model's parameters, epsilon, which controls the elasticity of commuting flows to commuting costs. We're also going to report a comparison of the changes in the values of land and buildings from constructing London's 19th century railway network to the historical estimates of constructing those railways. And there we're very fortunate that the House of Commons had a number of parliamentary commissions which reported detailed estimates of the costs of building railway lines. And so we distinguish between the costs of building cut and cover underground railway lines using statistics reported by those parliamentary commissions. And the Parliamentary Commission estimates those as around £350,000 per mile in 1921 prices. The same commission reports separate estimates for the cost of building bored tube underground railway lines like the Northern Line, which are obviously much more costly to build. There, the costs are around £550,000 per mile. In contrast, overground railways are obviously much cheaper to build. We estimate those at 60,000 miles per line based on other government statistics reported in the railway returns. And obviously for the parts of the underground network that are above ground, we treat those as being exactly like overground railways. You know, the parts of, for example, the District Line, which would run on open ground, they're above ground. No cut and cover techniques were required. No bored tubes were required. So now what we're doing is we're starting in 1921 with a very similar methodology to before, but when we go back in time, instead of letting productivity and amenities change in the ways that match the data, we hold in the model without any agglomeration forces and no change in the supply of floor space, we hold productivity, amenities, and the supply of floor space exactly constant. And so here I'm showing you a comparison with our earlier analysis. What am I showing here? Net commuting into the City of London back to the early decades of the 19th century. The black line were our earlier predictions when we conditioned on population and the value of land and buildings back into the 19th century. The light gray solid line are the predictions of our models when we hold everything constant at its value in 1921. We say the supply of floor space would be unchanged, productivity and amenities would be unchanged. The only thing we did is remove the railway network. One really interesting insight from this is that much of the increase in net commuting in the data is really driven by this pure change in commuting costs. Even when we hold productivity and amenities constant, net commuting falls from around 380,000 into the City of London to around 100,000 in 1831. And that's consistent with a bunch of evidence we present that without the railway network, it would be really, really difficult to have huge separations of the number of people living in a place and the number of people working in a place. What are the other counterfactuals? Well, in the other counterfactuals, we progressively perturb assumptions of the model. First one we say is, well, let's start in 1921, but instead of holding floor space constant, let's allow the supply of floor space to respond with our estimated floor space supply elasticity. Those are the black dashed lines with circle markers. Next thing we do is we introduce agglomeration economies in production with our estimated parameters. They're the gray dashed lines with circle markers. The very final exercise we do is we then further augment that by allowing for agglomeration economies in residential choices, and that's the dashed black line with triangle markers. And as you can see, those magnify the removal of the transport technology, and I think that's an extremely important insight that comes out of our paper, which I think economists have neglected, and I think planners have paid much more attention to, which is that the value of a transport improvement depends crucially on the complementary investments you make in the built environment. And so the endogenous response in the supply of floor space is in particular a big force for magnifying the impact of the transport network in our model. And that's a very important insight you'll see in several of our findings that I'll show you in the next couple of minutes. Another insight is that it's very important in cost-benefit analyses to take into account agglomeration economies. They also act as a magnification force. And you see that here to some extent in the fully loaded model, we actually predict slightly bigger effects from removing the railway network than in the earlier baseline analysis. Here's the impact of removing the underground alone. Even that is kind of quantitatively substantial, but obviously much less extreme than removing the entire railway network. And then, you know, one of the things where I want to spend most of the rest of my remaining minutes or so is where we use the model to generate counterfactual changes in the value of land and buildings. We then compute the net present value of those changes in the value of land and buildings, and we compare them with historical estimates of the cost of constructing the railway network. And so this are the counterfactual predictions for removing the whole railway network under different assumptions. Column 1 is exogenous supply of floor space, constant productivity and amenities. Column 2 allows the built environment to respond, endogenous supply of floor space. Columns 3 and 4 first introduce production agglomeration economies, and then in column 4, both sets of agglomeration economies. These are the implied changes in the net present values of the value of land and buildings. So these are the implied changes from removing the railway network, so they're all negative. These are the implied savings in construction costs if you didn't construct the railway network. So these are the estimates per mile multiplied by the number of miles of the relative type of railway line. And then the very final panel of the table, we report the ratio of the change in the net present value of land and buildings to those historical estimates of construction costs. Obviously, this is not a full cost-benefit analysis because we're not taking account of the costs of running the railway network or the profits you might make or any environmental externalities and so on. But nonetheless, it's interesting to compare the changes in the implied value of land and buildings to the estimated construction costs. And as you can see, we actually find ratios substantially above 1, which was sort of rationalize the construction of London's 19th century railway network. But again, one very important insight is those ratios are much bigger once you take into account that when you build the railway lines, people are going to build buildings in response, and that increases the value of those transport investments. And it's very, very important to take that into account quantitatively. And then we do something similar for the underground railway in the paper, and you can see the paper for more evidence on that. But let me try to conclude to leave some time for final discussion. What did we try to do in the paper? Well, modern metropolitan areas involve immense concentrations of economic activity, moving millions of people around each day. And we tried to assess what role does the ability to separate where people live and where they work play in understanding these concentrations of economic activity. And the key idea is to sort of use the invention of the steam railway as a natural experiment. That before that dramatic improvement in transport technology, it was very hard to separate where people live and where they work. We find substantial effects of that new transport technology. We find that our model is sort of remarkably successful at explaining the reorganization of economic activity you observe in London following the new transport technology. So the specialization of the center as a workplace and the suburbs as a residence. Just from removing the railway network, we find commuting into the City of London alone falls from around 370 to 80,000 to around 100,000. We find there's very, very important endogenous response in the value of land and buildings to this transport technology that magnifies the impact of the new transport technology, as does allowing for agglomeration forces. And for our baseline estimates, we find that the increases in the net present value of land and buildings exceed historical estimates of construction costs, and in many ways sort of validate the construction of the 19th century railway network. As you'll see when you read the paper, we obviously find the railways added in the very final years of that network were less valuable than the very first railways added, but nonetheless, overall, the increases in the net present value of land and buildings exceed the construction costs for plausible assumptions about discount rates. And I should stop there to leave some time for discussion. Thank you very much.
Thank you, Steve, for this very clarifying empirical and section and counterfactuals. These numbers are very striking. So we really can gauge the value of such a investment in transportation. I mean, the last few minutes, I will try to summarize two sets of questions that sort of appeared during the talk. Before doing this, I would just like to say that we are going to post on the chat, on the Q&A box, the link for the after session, which starts immediately after. So if you have questions that have not been answered in this session, maybe you can participate later, ask them directly to Steve. So I would just like to read, to open one argument, this comment from before. Speculation of land has always happened due to anticipation of future benefits in Japanese metropolis, including Tokyo, Osaka, and Nagoya in economically growing days, particularly in the 80s, and has led to a bubble economy. In the latest period of the 80s, the total land asset value became twice more than that of the US. From this point, I would like to add the previous question that was asked about event studies, saying, should event studies also account for anticipation? It seems that Crossrail has increased house prices ahead of completion. I would just like to use these two questions and then maybe build upon them later if you already have an immediate answer to this argument.
Yeah, so it's a great question. So let me go through, take the event study one first. Sorry, too many slides at the end, but oops, right, where do I go back to? So great questions. On the event studies, we actually find that once we allow for separate time trends for these locations, there isn't much evidence of anticipation effects. So, you know, that we find this is pretty close to zero, it's pretty flat, it's not statistically significantly different from zero. There's a very small curve upwards here, but not statistically significant. So once we control for the fact that, you know, some places have higher trend rates of population growth than others, we don't find, at least statistically, we can't discern any evidence of anticipation effects. It is true that one feature of our estimates is that these effects of the railway continue for many decades afterwards. And so, you know, one thing you could think there is that there might be some sort of dynamics to the accumulation of buildings over time, that it takes time to build railways, to build houses in response to the railway. And so actually in the paper, we actually have a dynamic model where we develop a model that allows for that. And we actually show that the baseline way we take the model to the data is in fact consistent with allowing for some gradual adjustment as you gradually improve the housing stock in response to the construction of the railway network. And the intuition for that is there's indeed a gradual response, but it's captured in the observed population and rateable values. But I think it's definitely true that the construction of the buildings is very complementary. In principle, you could think there could be speculative construction in advance. At least in the London setting, we don't find that much evidence of it, at least on average. I've done some reading on the history of London. I think that's generally true, that when you read about London, you read a lot of discussion. For example, there's a historian, Dios, who has a very famous study on Camberwell, where he actually finds that the railway coming to Camberwell kind of precedes the construction of housing for quite a couple of decades, and there are kind of open fields around the railway for a number of years. In principle, you know, there could be some anticipation effects. We just don't really find that much evidence of them in London in our event studies. In terms of, you know, the valuation of land and buildings, and more generally, as I said, I think it's very important, and I think it's underappreciated in economics, this idea of the complementarity between investments in transportation and other kinds of investments, like investments in buildings and structures, machinery and equipment. The way we've written down our model, we don't really have a way of thinking about bubbles or speculative rational bubbles. There are economic models that do try to rationalize bubbles. I think that's something that would be interesting to think about. It's not an area of economics where I myself have worked. You know, when valuing these transport infrastructure improvements, you'd want to value them using land values that you think are not distorted by bubbles, because you want to try to capture the fundamental value of these structures. And so we've taken the stand that in the data, the values of land and building that we reflect, that we measure, are really market values, which they are meant to be market values, and that they capture the fundamental value of these locations. And there wasn't really a large, you know, large-scale property bubble for London. And of course, you know, some neighborhoods experience rapid increases in house prices during our sample, but the way we rationalize those is that they were related to this improvement in transport technology and the complementary investments that took place. And so they reflected changes in the true economic value of the locations. They weren't pure speculative bubbles. But if you thought there were pure speculative bubbles, then you'd want to sort of have a model of the fundamental value of locations and use that fundamental value rather than the bubble inflated value. So, but great questions.
Thank you for the clear answer. If I may rebound on what you just said without having you to repeat yourself, do you happen to have any historical evidence on the sort of land market structure that was in place in the 19th century? I'm thinking about this paper by Henderson and Mitra in 1996 that talks about the existence of edge developers who are large players who by themselves allow the expansions of the city and compete with the existing centers that maybe have a more of a perfect competition situation. What would be your thoughts on this argument?
Yeah, it's a great question. I didn't emphasize it today, but I sometimes do. And I'm, say this with trepidation because I'm speaking to an urban planning audience today, and so you all know much more about this than I do. But another empirical strength of our setting, we think, is that London in the 19th century is exactly a setting where market forces are likely to apply and where land potentially could be easily reallocated to alternative uses. And so in particular, for example, urban planning, large-scale urban planning in London doesn't really get going until, at least my understanding and from reading quite a bit of planning literature, is it doesn't get going until the Barlow Commission of 1940. So a famous book by Foley, Planning the Great When, which discusses this in quite a lot of detail. And so one of the nice features about our framework is that land markets and the demand for land could largely reflect market forces. Of course, some of this land was owned by large-scale landlords who owned large swathes of territory, for example, the Duke of Bedford, the Duke of Westminster, and so on. One distinctive feature about London is that when these areas were developed, they were developed under what's called a leasehold structure, typically where the land was, a lease to the land was sold, which enabled builders to actually build the houses, but the landlord retained the freehold, so the Duke of Bedford or the Duke of Westminster retained the freehold. Again, I think that works towards a market structure because what it meant was that small builders could build these houses and could build them relatively quickly without having to sort of buy a huge swathe of land and purchase the freehold, or without the Duke of Westminster having to sink this huge risky investment into constructing the houses himself or herself. So I think it's a reasonable approximation to say that market forces operated in the Greater London area. Of course, there were some local regulations. The City of London was responsible for the city. Before the Metropolitan Board of Works in 1855, the parishes and vestries had regulations over land use and land structure. But the word of well-defined property laws, England has had a long tradition of common law. There were active property markets, active rental markets. And so I think it's actually a strength of this setting that market forces could operate. And in fact, when you read the history of London's development, it's very much emphasized that haphazard organic development, whereas cities like Paris, where Hoffman and other large-scale players, typically influenced by government there, played a larger role. And so at least my understanding is there weren't any, well, the closest to a large-scale property developer in the Henderson sense, at least to my understanding, was the District and Metropolitan Railway, which is actually an exceptional case for railways where the Act, as far as I understand it, the Act of Parliament included some land for the railway. And the railway company itself actually played a role developing what it called Metroland. And so that's the closest case in London to there being anything like Henderson's property developers. Otherwise, I think it's a reasonable approximation to think that market forces played a big role in the development. Obviously, some individual landowners were influential, but I think the way the leasehold system worked, it sort of militated towards market forces this city developed.
Thank you. This was a great answer, very illustrative of the forces that underlie the developments of the city. I will have, in the interest of time, one final question that summarizes the other set of questions that we received, which is in the difference of transport measures, so rail versus road versus car. In particular, I'm reading one question as appear. Any consideration of the impacts of rail investment today must include representation of travel possibilities provided by the private vehicle. Would it be possible to try a counterfactual with your model to reconsider the impact of rail in London from 1841 forward with the car also available?
Great question. So one of the reasons we kind of picked this empirical application is firstly, London's unusual in having this historical data going back in time. And secondly, we have that detailed bilateral data from 1921, which is very, very unusual. And thirdly, that largely predates the car. And so it could really isolate the effect of the railway network because according to the data reported by London County Council, private car ownership in London was extremely rare, like less than 0.01% of the population, according to registered motor vehicles in the London County Council area. And so it really enables us to really isolate the effect of the railway, which is the whole experiment we wanted to focus on. I think the car is also super interesting one thing we've been debating is, you could argue that in some ways you could use the same model, but the effect of the car might be different, in the sense that railway networks are very infrastructure heavy because they're very reliant on large networks of railway lines, of stations, of goods yards, and so on. Whereas the car is relatively infrastructure light. You do have to build roads, but you don't have to have a fixed infrastructure. Cars can move through side roads in a very kind of decentralized lateral way. And so you might think that the car would be much more decentralizing than the railway. So that would be a difference. And I mean, that shouldn't affect using the model. You can use the same model and take into account what the car does to travel times. It's just that because for the car you have all these lateral connections through these side roads that you don't really have for the railway. The changes in travel time implied by the arrival of the car will kind of help to decentralize, because you'll be reducing travel times between peripheral locations much, much more. So I think that would be an implication of moving towards the car, is that the car should be an even stronger decentralizing force. Although I should just sort of flag that even here for the railway, while the biggest absolute increase in employment is in the City of London, as we saw, if you look in percentage changes, we actually find decentralization even for the railway, in the following sense. The gradient of economic activity here is flatter under the railway. And in percentage terms, the biggest increases in employment by workplace are actually in the suburbs, because the initial levels are so low. So I think you absolutely could use the car. You definitely need the full road network, and it's going to change travel times bilaterally much more than the railway does. The railway really helped favor the center. So the car will help to decentralize, but absolutely there's no reason you can't do that. One way of doing it would be, for example, to build in a modal choice model that transportation economists use. You could definitely nest that in this whole structure here by having a modal choice. And in fact, in the paper on Berlin that I mentioned earlier on the economics of density evidence from the Berlin Wall, we actually use a travel modal choice like that, where we do take account of the car.
Thank you, Steve, for this final answer, which concludes our official session. And I posted the link of the after meeting session in the chat. You also received it in as the second link in the email you received about the talk. So please join us for a free conversation. Thank you, Steve, for your time. And
thank you. I'll be there for the general conversation in 5 minutes. So I'll be there in 5 minutes.
Of course.
Thank you very much for all the questions and discussion. It's been really fun, and it's great to have this opportunity to interact across disciplinary boundaries. And if anyone has any questions or would like to follow up by email, that would be terrific.
Thank you. Mike Batty passes his greetings and congratulates you on the presentation.
Thank you. I
will now.
Mike had to leave, because well, actually to another meeting. Yeah, so great to have this, and so I'm really pleased that there is seems to be the meeting of minds actually between these different realms, and we really hope that this kind of development will then continue. And again, at the very last, what I like to do is to thank Professor Steve Redding for really a fantastic lecture, and also the way that Dr. Jamil Noor actually has interacted. And I also like to thank the student supporters, Shanshan Xie and Yue Ying, and also our colleagues in Shenzhen University, Professor Yue Yang and her students, actually supporting us actually for getting this information to a wider audience. Right, so for those who like to join us for the post session, and we look forward to seeing you there. So yeah, they will have okay, so this is in the chat box already. So, or actually for the participants, they will have got the invitation in the email as well. So see you there. And Steve, take a breather and perhaps have some water, and I'll see you there if you are still able to join us. So
I look forward to seeing you in 5 minutes. Thank you again. It's been really fun. And thanks for all the feedback.
Yeah,
Okay,
great.
bye.
Yeah,
Bye.
and well, I think you have to press the button now actually too. And Shanshan with Billy, I think that's it, right? So we don't have to do anything more. Yeah, excellent. Well done. Thank you so much for staying till 1 o'clock. So, and have a good evening.